Okay, so today we're going to begin our discussion of rotational motion. And I'd like to start everything off by showing a demonstration between the difference between circular motion and rotational motion. So let's watch this video here.
In the previous video, we studied what motion is. We also saw one type of motion called the rectilinear motion. It's nothing but straight line motion. In this type of motion, the path of a moving object is a straight line. But what if the path of a moving object is circular? Yes, you guessed it correctly. If an object is moving in circles, it's undergoing circular motion. More accurately, it's defined as the motion of an object along the circumference of a circle. The circumference of a circle is the length of this boundary, which is curved. So if an object is moving along the circumference of a circle, we say it's undergoing circular motion.
Cool.
Can you give me any real-life examples in which objects execute this type of motion? What about the satellites orbiting the Earth? Yes, a satellite orbiting at a certain height is also undergoing circular motion. What other examples of circular motion can you think of? Take a small object and tie it to one end of a rope. Take the other end of the rope in your hand and whirl it around in circles. You see that the object is performing circular motion. Notice that the distance of the stone from your hand is always the same. What about the moving fan? Is it also undergoing circular motion? First, let's only consider the motion of a point on one of its blades. If we switch on the fan, we will see the point moving in circles. So we can say that the blades of the fan are also undergoing circular motion. Now what if I take the fan as a one single object? Can I say that the fan as a whole is moving in circles? No, that would be incorrect. The fan as a whole is not going anywhere. The entire fan is not moving along the circumference of a circle. But which motion is it performing then? The fan is undergoing rotational motion. Before actually defining this type of motion, let's try to understand it first. This rod here is called the axle, and the entire fan is spinning around this axle. Or you can also say that the entire fan is spinning around this fixed line. This type of motion is...
Yeah, so I mean, you can just imagine that if the fan was moving in circular motion, that the entire fan would be going around in a circle as opposed to staying fixed on the axle and spinning in place. So I believe you get that point.
What we call rotational motion. Now we will define it in simple words. A body is said to be performing rotational motion if it's spinning around some fixed line. And the fixed line is also called axis of rotation. What other examples of rotational motion can you think of? What about a rotating wheel? We use the word rotating because it's performing rotational motion. What is axis of rotation in this case? Yes, it lies on the axle of the wheel. So the wheel is also undergoing rotational motion about this fixed line. Other examples of this type of motion can be the Earth spinning around its axis and a spinning top. But wait a moment. Let's go back to our example we discussed earlier. When this object was whirled around in circles, we said that it was performing circular motion. But here, if we take this line as our axis of rotation, then we can also say that the object is performing rotational motion around this fixed line. So what is the motion of this object? Circular or rotational? What exactly is the difference between the rotational and the circular motion? In all the examples of rotational motion that we saw, the axis of rotation is a part of the object. It is going through the object. But in this case, the axis of rotation is not passing through the object. It's totally separate from the object. Hence, we don't call this motion as rotational motion. This is circular motion and not rotational. So this is the difference between circular and rotational motion. If a body moves along the circumference of a circle, we say that it's performing circular motion. And if the body is spinning around the fixed line called the axis of rotation, and if that axis of rotation passes through the body, we say that it's undergoing rotational motion. In the next video, we will see one more type of motion. See you there.
So we're just on our way to see the villa. Are you excited?
Sorry about that. Okay, very good. So again, circular motion just involves one particle going around a circle, and rotational motion is a fixed body rotating around an axle or axis of rotation. Okay, so let's go on to our notes here. So this is just a reprise of what we saw before. We're going to make the translation from linear kinematics to rotational kinematics. Back in the previous chapters, we have been dealing with a point particle. And if that particle is changing position from an initial position xi to x final, and the difference between the two, if we take the difference between the two, that would be a displacement, a linear displacement, given by this equation, delta x equals x final minus x initial. The velocity is how much time it takes to change that position, or the rate of change of position, delta x over delta t, linear. And linear acceleration is delta v over delta t. And then here are kinematics equations, which we're familiar with over here, along the x-axis. And then along the y-axis, the delta x becomes delta y, and the a becomes negative g. For rotational kinematics, we have a translation from linear to rotational motion. So anyway, in defining terms like the length around the circle, we call an arc length, which takes similar properties as a linear distance that we're familiar with. So if we're on a sphere or spinning top or a fan, as we saw in that previous video, and we take a look at a particle on the outside of this circle, we know that it's going to go around the circle in the circumference that we know as 2 pi r. But in this picture, we're taking a look at where the particle is at this point, and the distance that is traveled from 0 is called the arc length. This arc length is equal to the radius of the circle times the angle subtended by the radius and the horizontal axis. Our convention is that we're going to spin around counterclockwise. Counterclockwise is considered the positive motion or positive direction. So counterclockwise rotations are positive directions, and conversely, clockwise rotations are the negative direction. So this distance, which is similar to x in linear kinematics, s is equal to r theta, our arc length is equal to radius times angle. The angle theta is in terms of radians because we have meters divided by meters, arc length divided by radius, and we get a unitless number that we call the radian. If we go around the entire circle, one revolution is equal to the circumference of the circle, which is 2 pi r, and we have radius r, and thus for a full circle, theta equals 360, we know that angle theta can be re-expressed in terms of 2 pi radians, which of course is 360 degrees. So the true revolution around the circle, the complete arc length of the circle, the circumference that is given as 2 pi r divided by r, 2 pi radians, 360. Degrees can be commonly talked about in terms of radians. So we can define the radian as 360 degrees divided by 2 pi, which is just this bit of the equation here, 360 divided by 2 pi radians, which is equal to theta, and that theta will be 57 degrees, 57.3 degrees. So 1 radian, 57.3 degrees, and vice versa. We know already from geometry or trig that we can convert an angle in degrees to radians by using this conversion factor. If 2 pi radians is 360, half of that pi radians is 180 equals theta. Thus, if we have an angle of 60 degrees, we can convert that to radians using the conversion factor, pi radians over 180, we get pi over 3, or pi radians over 3, or pi over 3 radians, whatever. Okay? Now, in this picture here, I think I'd rather redraw this and just talk about it real time. Okay, so let's take our circle and we have, let's say at some point in time, we're going counterclockwise. We're traveling the distance around a circle in terms of the unit circle convention. At some initial time here, the particle is at some initial theta. And then at some time later, particle is at theta final at t final. And so thus, we're not going to be talking about linear displacement in a straight line or a vertical line. We're going to talk about angular displacement around the circle. So this is going to be theta initial here, and this here will be theta final. So much like linear displacement is a final position minus initial position on a line, the x-axis, we can see that the angular displacement around the circle looks similar to this, as this theta final minus theta initial gives us the angular displacement. So this is linear displacement. And this is angular displacement. All right. And then we also know that velocity, as we saw up top, is going to be linear displacement divided by time. But now on the circle, the time it takes to change angular position, or the rate of change of angular displacement, is going to be called our angular velocity. So we make a substitution, and instead of v, we're going to call angular velocity omega. And that equals to delta theta over delta t. And so let me separate these. And of course, this velocity in terms of the circle is going to be on the outside of the circle. So if we take another look at the circle, as we are rotating, this linear velocity will be called the tangential velocity, or the velocity on the outside of the circle. Particles here and there, and still going around in the counterclockwise fashion. And the angular quantities, so the linear quantities exist on the outside of the circle. But the angular quantities, the angular velocity, and then later on the angular acceleration, and then other quantities like torque and angular momentum, those angular quantities are fixed about the center. And so we'll see a little bit more treatment on that in a moment. So linear velocity, tangential velocity on the outside of the circle, angular velocity is with respect to the fixed axis, omega. And we'll be making a translation between the two shortly. Before we do that, let's move on to a tangential acceleration and angular acceleration. Let's say we had an outside force that was going to increase the speed around the circle, increase the magnitude, even as the direction is changing. We have a tangential or linear acceleration of the particle on the outside of the circle. That's going to be equal to change in velocity over change in time. And then the angular quantities, the angular acceleration is going to be with respect to the center of the circle. So we say alpha is equal to delta omega over delta t. So linear acceleration, delta v over delta t. That's on the outside of the circle. If we're just, keeping our focus on a sphere that's rotating about an axis, the linear acceleration exists on the outside. The tangential acceleration is on the outside. And it's going to be equal to delta vt over t, or just delta v over t. The analog, the rotational analog for linear acceleration would be the angular acceleration here, which is equal to change in angular velocity over change in time. So that looks something like this. Circle counterclockwise. And we have tangential acceleration like so. And the angular acceleration is going to be with respect to the fixed axis, whereas the linear acceleration is on the outside. That's changing this velocity, the tangential velocity on the outside. And of course, we're only going to have a tangential acceleration if there's an outside force. That outside force is going to be important later on as we talk about the concept of torque. All right. So just to finish this up, this will be our linear acceleration. And this is the angular acceleration. Okay. Those are just the straightforward analogs between the two. There's a linear acceleration equation and there's an angular acceleration equation. So now what I want to do is just to marry both concepts and see them all at once. Okay, so we have the basic equations down. We have the rotational, the kinematics equations. We know what the linear kinematics equations are. So let's just see how they relate for an object under rotational motion. Okay, so let's redraw the picture of a particle on a sphere, for example, in rotational motion, and describe the marriage between linear velocity around the circle and the angular velocity of the sphere, and then we'll go into the linear and angular accelerations. All right. So again with this unit circle. Let's say we have part of the circle that looks like this, radius r, with any arbitrary point P experiencing a tangential velocity at linear velocity around the circle. And of course, as we described earlier, this will be like the arc length. So it's, coming from, theta equals 0 to whatever theta here, and then so on and so forth. So we know that S equals r theta for a distance, or small distance around the circle. Approximate that to some linear distance of around the circle. It's approximately linear. S being the arc length or linear distance. More accurately, our linear position. Point P at that point. Now, of course, if we said S sub I, which is equal to 0 down at the bottom here, and we come up to some final S, and apparently that would be our delta S. And the time it takes to do that, to change from Si equals 0 to S final equals something that's not 0, we'll call that our linear velocity, which is what we're going to describe next. So the linear or tangential velocity, which is going to be delta x over delta t, as we saw up top, which is basically the same for a circle, delta s over delta t. And since s is equal to r theta, then delta s is going to be r delta theta over delta t. Since s is r theta, our angle is changing. We're going to look at how the angle is changing. And of course, this arc length is changing as the angle is changing. So this is our equation, r delta theta over delta t. And we defined up top that delta theta over delta t is angular velocity. So tangential velocity is married to angular velocity by this equation, r omega. So again, vt radius and as defined up top, the angular velocity will be with respect to the fixed axis. All of the angular quantities with respect to the fixed axis of rotation. Angular velocity, angular acceleration, torque, angular momentum, etc. So likewise, when we let's say we had an outside force that's going to accelerate the particle around the circle, so the magnitude of Vt changes. So therefore, we have a tangential acceleration, and that's going to be given as At equals delta V over delta T. Well, V is equal to R omega. So delta V is just going to be R delta omega over delta t, where delta omega over delta t is defined up top is angular acceleration. So that becomes our alpha. Our condensed tangential acceleration is going to be radius times angular acceleration. So if we had the same situation, circle, there's an outside force over a radius, a torque, an outside torque, that's going to change the velocity around the circle, and we have a tangential acceleration, something like this, radius, and theta, and so forth is s. And so the tangential acceleration is on the outside, the angular acceleration is on the inside at the axis. So in this configuration, the rotation is counterclockwise. And as we defined up top, even more, the counterclockwise rotations are positive directional rotations. And if we went the other way, you know, if we had the circle, the tangential velocity like this, moving in a clockwise rotation, then well, clockwise rotations are going to be always negative. So anything with the angular quantities, where there's angular velocity, acceleration, torque, angular momentum, if that angular quantity is undergoing a counterclockwise rotation, that means that that quantity is positive. Counterclockwise, positive angular acceleration. Clockwise, that's going to be considered negative. Let's move on with this definition of tangential acceleration that we just defined up top. Our alpha. Now, even though this fixed body, this sphere, or this wheel is undergoing a rotational motion, if we look at the particle on the outside of the wheel, we can also take a look at that particle undergoing centripetal acceleration as it rotates about the axis. So there's going to be a radial acceleration or a centripetal acceleration, as well as this tangential acceleration. So we have a situation that looks like this. Let's say we have a tangential acceleration as well as a centripetal acceleration. We know by definition that centripetal acceleration is v squared, or technically vt squared over r. And we know that vt is r omega, so r omega squared over r. And so another way of expressing the centripetal acceleration in terms of the angular velocity or angular quantity is given below. So these are all the same thing. Okay, and we know this form already, vt squared over r. So we define the counterclockwise rotations as positive and clockwise rotations as negative. There's something called the right-hand rule, where we can determine the actual directions of the angular quantities with respect to the plane of this page you're looking at. Let's talk about that for a second. So let's see. Again, some sort of circle, a record player, or sphere, or wheel rotating about a fixed axis. Let's say that it's rotating clockwise. We know that, for example, if this sphere has a constant tangential velocity, the magnitude doesn't change, but the direction changes. We know that there's a centrifugal acceleration, all that good stuff. But in this configuration, if we have this clockwise rotation and the linear quantity in question is tangential velocity, we know that the angular quantity associated with this tangential velocity is our angular velocity. We can determine the direction of the angular velocity vector using the right-hand rule. And we can see exactly what is meant by a positive counterclockwise rotation or a negative clockwise rotation. What does that signify? So clockwise rotations, again, are negative. And employing the right-hand rule, where the fingers, the four fingers, not your thumbs, but the other four fingers, the fingers represent the rotation. And your thumb represents the angular vector or angular quantity, in this case, angular velocity. If you curl your four fingers in the direction of this arrow, let me take a couple of practice trials there. You will notice that your thumb points into the plane of this page. When an angular quantity points into the plane of the page, that is your negative direction. So we get some more, kind of visible understanding of what is meant by negative direction for angular quantities. So in this case, it's a clockwise rotation, negative. That means that the angular velocity is going to be pointing into the plane of the page, or omega n. And we typically denote that symbol, like you probably see that in your problems or someplace in your book, that the angular quantities are going to be represented by an X. Just imagine an arrow going away from you, and you're seeing the back part of the arrow, which is usually like some, forming an X. Crosshairs of the arrow. So when the angular velocity is pointing in, that is negative clockwise rotation, negative direction. Now, if we take the same circle and go counterclockwise, so here again, and then let's say that our tangential velocity is in the other way, to go counterclockwise all the way around. Again, your fingers, just kind of separate this. Your fingers represent your rotation. Your thumb, once again, is the angular quantity. And this may be a little bit easier. You curl your fingers, your other four fingers, that's not your thumb. Curl your fingers in the same direction as this arrow. You will notice that your thumb points out. That's the positive direction of angular velocity when it's a counterclockwise rotation. So counterclockwise rotations. It's, you know, positive. You know, positive direction of angular quantity. And this time the arrow is coming towards you. So angular velocity is pointing out of the page, represented by a dot, because that's the arrowhead coming towards you out of the page. This is the positive direction. That's what's meant by a positive direction when a quantity undergoes a counterclockwise rotation. When it spins counterclockwise, the angular vector will point out. Clockwise, the angular vector points in, and that's negative. It's going to be very important when we get to torque. So if we have a counterclockwise torque, that torque is going to be positive. We have a clockwise torque, that's going to be negative. So any angular quantity, that's why I just generalize as angular quantity. That can be angular velocity, angular acceleration, torque, angular momentum. If any of those are counterclockwise, that's a positive direction, clockwise, negative. And the symbol usually represented by this dot to represent like an arrow coming at you. And if it's inside or negative, it's like the arrow is going away from you into the page. That's why in, W or omega in. Omega out, positive. So we had a bit on that. I want you to take a look again back. I guess both of these pictures. Notice something, at least the visible, the geometric relationship between tangential velocity and the radius. There is a 90-degree angle that's formed here. You know, they construct a 90-degree angle between the two, between tangential velocity or the linear quantity on the outside, linear velocity, and the radius. There is a linear acceleration forming a 90-degree angle with the radius again. What causes accelerations? Well, forces, net forces cause them, right? As we recall back in our analysis of forces. So let's take the same sphere. We have, you know, like imagine a wheel that's spinning, going at a constant rate, and then you just push the outside of the wheel with your hand and make it spin even faster. You've now accelerated it. You've given it a tangential acceleration by the application of your outside force. And so therefore, circle again, and let's just, you know, keep it simple here. Let's apply this outside force at this point, or external force. And this is my radius, 90-degree angle. There is a new quantity, a new angular quantity that is formed as a result of the external force here applied at a 90-degree angle to the radius. It has the similar relationship as tangential velocity to radius, which is perpendicular, tangential acceleration to radius, which is perpendicular, and now we have our external force, which causes that tangential acceleration, also perpendicular to the radius. The new quantity, angular quantity here, which is the multiplication of force and radius, that particular force that is perpendicular to the radius is called torque. So tau is torque or angular force. We have angular velocity, angular acceleration, angular force, and this angular force or torque is also with respect to the center of the circle, or or at the axis of rotation. And yeah, we're going to pretend like a rod is coming out of the plane of the page, you know, and it's spinning. In this case, it's going to be spinning counterclockwise or clockwise, whatever. So that is the basic definition of torque. As with forces, they don't always form nice perpendicular angles to the radius. It can be at any angle. So what if we had a situation, a radius again, and let's say we had a force that was at some angle. Well, the torque would just be the part of this force that's perpendicular to the radius. In this case, that would be the sine part. F sine theta is perpendicular to the radius. Okay, extend our radius out and like that. So then our generalized torque equation is net torque is equal to F sine theta times R. And it all goes back to our definition where we start establishing this, this relationship between linear and angular quantities, where we have Bt is equal to R omega, multiplications. Linear acceleration is equal to radius times your angular acceleration, and torque is going to be your outside force multiplied by your radius. And we can rearrange this around Fr sine theta. So it has a similar look and feel to work, where we know that work is equal to F cosine theta delta x. Of course, R is not a change, it's the same, the radius doesn't change, but it has the same, similar look. And this particular equation is formed due to what is called a cross product between force and radius. So what I mean by that is taking force looking like this, and then we have let's say the radius, you know, we're going to point it towards the center of the circle. When you multiply these two vectors to form torque, another vector, what you're doing is you're taking, let's say, pretend that your four fingers are in the same direction as the external force. The radius will be your palm. Okay, just imagine that there's a line coming out of the palm of your hand. You got to point your fingers up. There's an imaginary line coming out of the palm of your hand that should be pointing to the left, like the radius here. And when you curl your fingers towards the left in a counterclockwise fashion, like the arrow, your thumb is going to be pointing out. So in this case, counterclockwise rotation yet again, the torque is going to be positive, in this case for counterclockwise rotations. A counterclockwise rotation, or in this case, a counterclockwise cross product between the vectors force and radius. But just think about it simply, if you will, in terms of this is just a counterclockwise rotation around the circle, like so. We're going counterclockwise. Okay, everything nice and neat. Okay, torque's coming out of the page. Positive, positive, positive. So in true math speak, this looks like this: F cross R sine theta. Whereas back in the day, we had net work is equal to F dot delta X cosine theta. So both multiplications are just two different kinds of multiplication. We won't get into the details of that here. So when you have a cross product, you always are going to form a new vector. When you have a dot product, you're going to form a scalar, because work is not a vector. It can be positive or negative, but it's a quantity, it's a scalar. Torque is a vector because it's formed as a result of a cross product between force and radius. And it's going to be the sine component of the force crossed with the radius that forms torque. And whereas in work, we're looking at the cosine part of force with displacement to create work. And that force can be either parallel to displacement or anti-parallel like friction. So that's the basis of torque there. And so yeah, going back here, if angle theta is equal to 90, we know sine of 90 is 1, it just becomes F times R. So for any other angle, generalized angle, this is what we get for torque. Generalized torque equation. Okay, for our last bit here. Say we have a rod and apply forces counterclockwise and clockwise. So again, counterclockwise is positive rotation, clockwise, negative rotation. Well, that rotation is considered negative. Counterclockwise rotations are considered positive. All or any angular quantity that's undergoing a counterclockwise rotation is a positive quantity, and vice versa, clockwise is negative. So let's put this rod here. It's rotating about some fixed axis. Let's say here, nice and neat in the middle. And let's say if we had F1 at this point, and then we had R1, it's going to form a torque because force times crossed or multiplied by radius gives me a torque. But I have another force over here. And if I just look at this force by itself, it's going to try and make a clockwise rotation. So this is going to try and make a counterclockwise, and this is going to make a clockwise at radius 2. Oop, much like, okay, much like, okay. Much like net work is a sum of different forces multiplied by displacement. So is net torque as a sum of multiple forces, one or multiple. So our net torque would be equal to the sum of both torques, which is going to be, let's take F1, R1, that's going to be a positive torque. Do that there. And then F2, R2 is going to be minus F2, R2. And so that will be what our torque equation would be when we consider the torques produced by F1, R1, or F2, R2. This is the linear combination. This is what it's made up of, and these are the so-called magnitudes and directions of those torques. And when you put your numbers in there, you're going to get a net torque. So if the first force, F1, is greater than F2, the net torque will be counterclockwise. And if F2 is greater than F1, net torque will be clockwise or negative or positive. And that's about it. That's the basics. And that's all in that. And we'll continue next time. And okay, yeah. Talk to you soon. One last thing. Okay. If you're watching this video again, which is a reprise of the notes, you want to read this first couple of sections of chapter 12. We'll be going into like the seesaw problem, taking a look at some forces and balanced torques. All right. And then, of course, later on, we'll be looking at unbalanced torques. Just like, at least the concept is just like forces. We're going to have like free body diagrams and force equations, but we're going to have an additional torque equation to deal with, because now we're going to be looking at things like, like before we had the pulley, which was massless and we ignored it. Now we're going to have to consider it, okay, with torques, because that's going to be the object that's rotating in the system. So concept of torque, introduced here. We'll be going a little bit further with it, a lot further with it on Monday. Okay, guys, take care. And God bless.